we're studying for the final, we'll just finish this package pretty much.
That's pretty much it. Yeah, your assignments through next Monday is finished packets, right? That's it.
Circle back. Like when we're studying for the final, like the final, we'll just be finished the packets then?
The final, you're talking about these ones coming up, you mean?
No, like
At the end of the year?
Yeah, so we'll just finish out everything in here.
Well, no, we'll have some new ones.
Okay.
We'll get some new ones. Okay, the question was when we get to the end of the year and final, and for those people that choose to take the AP test as well, our review is, the study is the packets. Now, what we'll do as we start going into integrals, it'll be a while, but a month from now, maybe, we'll start learning and have learned enough stuff that we can start to do some of these. We can start to finish some of that we haven't done. So we'll do that. We'll go through that process of doing that as gradually as we go. But then as we get closer to the end, we'll do some new packets. And the main reason we do some new packets is to go back and review this old stuff, right? Because we get 2 months from now, and all of a sudden all the derivative stuff's going to be like, wait a minute, what was that? Because we'll be so much into the integrals and stuff. So we'll have to really come back and review this old stuff. So that'll be the hardest part of it, to be honest with you. All right. So I want to start with number 7, okay? And I know a couple people had asked me about this one yesterday, but I do want to.
We can do number 11 too.
Okay. Was that the inverse one?
Yeah.
We can do 11. No, we're not doing 8. But I am going to talk about concave up, concave down. And 23 is another one I'm going to do. Okay? And I'm guessing you might talk me into a few more. But I do want to talk about 7, because this one is a little different take on something that we have done before. So it says a function g is defined from this property, and it's weird. You got a's and b's, but yet they ask you for g prime of x. So that's weird. But first of all, there's one overriding thing that is in most of these problems, that's derivative, right? And let's face it, the big thing we've done for the first half of the year is derivative. Most problems involve derivative. The only ones that would be maybe a few limit problems, because limits is another big topic, I guess you would say. They probably, if somebody described an AP calculus course, there's 3 big topics: limits, derivatives, integrals, right? Limits are kind of a piece of both. They're part of derivatives, part of integrals. So those would be the 3 big topics, with derivatives and integrals being the biggest, right? And then limits, there's a part of it. So every problem probably has something to do with one of those 2 at this point, because we haven't really done integrals yet. So when you look at this, is there anything in this that looks vaguely familiar? This side here kind of has a look like definition of the derivative. The x plus h business, right? And that's where you would start. Now, again, without ever seeing this, and it's hard to review for the final. It's hard to review for the AP test, the midterm. There are just so many different things to do. That's why we did 4 packets. I mean, the more things you do, because what the AP test is about is seeing if you really know the concepts. And so they ask you a lot of different questions that involve these concepts. And the idea is, if you really understand the concepts, you can put these into new and different problems and know what's going on, instead of just memorize, okay, on this problem, this problem, this problem, I do this, whatever. Okay? That's why we do it. And I think it works. I think it's good. Okay? So the more packets we do, the more often, I've noticed it already, you guys are going through them, and I think you're starting to see problems over and over, and you might be going, God, this is, geez, another one of these, geez, Christmas. But that's a good thing. If that's happening and you're recognizing and you're saying, yeah, God, I've done this before, I got it, okay, that's a great thing. You take calculus next year, even if you take Calc 1 over again, that's going to be a good thing, that you recognize all these things. You should do well, all right? Well, right here, what we would hope to be seeing is that that's definition of the derivative. So what I'm going to do to help you see that is write it down. So I would hope everybody could write down the definition of the derivative. It says right here, g prime of x equals the limit as h approaches 0 of g of x plus h minus g of x all over h. Now we did it with f of x, but hopefully we can make that transition at least. Now you look at the top of that, and you look at this, and you're like, yeah, that's kind of the same thing. Now the difference is they used A and B. So let's rewrite ours using A and B. So what would be in place of the X? A. And what would be in place of the 8? That would be B, right? It looks to me like this is the X, this is the H. Okay? So I'm going to rewrite mine as G of A plus B minus G of A, and then all over B. So now I look at this and I'm like, okay, now I see that this is kind of, I'm not paying attention to the right side right now. I'm just kind of looking at this, and I'm looking at this, and I'm looking at that, and I'm saying, well, what's this missing over here? It's missing an over B, so let's give it to it. Let's divide this side by B, but then of course we got to divide this side by B. Yeah, so now we can cross out the B's, and we get 4A plus 2B, right? So that's what we got so far. But now the left side still doesn't look like this over here. Quite. What am I still missing? I'm still missing the limit as B approaches 0. So let's do that to both sides. Let's do that to the left side, and let's do that to the right side. Well, what is the limit here as B approaches 0? That would just be 4A. The 2B would go away, because as B gets close to 0, we can just plug in a 0, and we just get 4A. Now, look at my left side up here. Now that's it. So the left side, now, instead of writing all that, I could rename that as what? G prime of A. So if G prime of A is 4A, remember the German shorthand stuff? G prime of X is 4X. That's kind of a strange problem, kind of a roundabout, goofy thing. But the idea is, I think the idea behind this question is that when you look at this and you're thinking, we're studying derivatives, that's the big idea going on here. They asked me G prime of X, that right there you would look at that and see the definition of derivative. Now maybe you would, maybe you wouldn't. But that's what you'd have to see. And then you say, well, what would I do to make it be the definition of derivative? And that's where that problem comes from. Now, just back up real quick, the more common one we've done is number 5. All right? If you go back to number 5, to me, this would be an easy one. This is the one we've talked about, that when you look at this limit, this isn't a limit problem. This is really what right here? That's G prime of X, right? That's just G prime. That's all they're asking you to find is G prime. They gave you G, so what is that? 1 minus sign? Bingo. That's one of those like 10-second problems I was talking about. You look at that, you say, oh, that's G prime. Just do the derivative. There's my answer. Okay, so that's one we're more used to seeing with definition derivative. 7 was a little bit kind of strange and unusual. All right, let's talk about 11, then we'll go to 23. Now, inverse functions. These always are tricky ones because they're ones we don't see very often. When we talked about inverse, now inverse doesn't mean reciprocal. That's important you understand that, right? That's the multiplicative inverse. That's what we're talking about here. We're talking function inverse, when you interchange the x and the y. Now, we learned about inverse functions when we did arctangent, arcsine, when we were learning those derivatives. That's when we did our work with inverse functions. One of the things we did, now it turns out you don't need it in this problem. But in a lot of inverse problems they ask you, you do. They give you one function and they ask you for the derivative of the other, of the inverse. Well, what it is, the rule for that is basically, it ends up being like a reciprocal of the input of the other one, or because you interchange the x and the y. But in this case, here's the first thing I would always try, is I would try to make this a y here, and then I would interchange my x and y. So I would make this x equals the cube root of y minus 1, and then I would solve for y. Sometimes it won't work, and then we'll have to do something different. But on this one, it will. So we cube both sides. We would add a 1. Wait, did I do that one? And so y prime would equal, yeah, there we go. Okay. I was looking up here and thinking this. Okay. That's a pretty easy version of the inverse, as long as you thought to do the inverse, right? To interchange the x and the y. Because what this is then is the f function, and then the derivative would just be that. What could I tell you if you couldn't solve that for y? You could do implicit differentiation probably. That would probably be the next thing you would do. Is you would interchange the x and y, because basically what they want to do, once you interchange the x and y, what we're looking for is y prime. So if you can take this function, interchange the x and y, then do the derivative with respect to x, find the y prime. If you can't solve for y, that's probably the next thing you would do. Okay? All right. Let's go to 23. Now, one of the things I'm going to talk about here also will help you on, I think it was the last packet we did, the last page. It was a problem asked about concavity and where the function's increasing. It's free response number 6, I think, on the third packet. Gets into some stuff like we're going to be talking about here a little bit. But it's got A's and B's in it. It's kind of like that problem we did a while back that had a K in it, or it had something. But anyway, here, let f be this function, and it says that f is increasing on what interval? What do we normally do when we want to check where f is increasing? We do derivative, but do what? We want to know where f prime is positive. Well, how do we find where f prime is positive? Set it equals 0 to a number line, right? Because you can't just find when f prime is positive. The way to find when f prime is positive is find when it starts being positive and when it stops being positive, which means at 0. Now, but it's more than just at 0. It's also an undefined. So what I want to show you here, real quick, is our chart. I think I put this up another time, but here's basically the chart. When we talk about local maximums of f, we talk about when f prime is 0, but we now know that it could be a sharp point too. You can have a local maximum when f prime is undefined. So our number lines from now on, our number lines really have to be where the derivative is 0 or where the derivative is undefined. Same thing with our number line for concavity, which this problem doesn't get into, but I'm going to talk about here in a minute. When you do a number line for concave up or concave down, you should also include where the second derivative is undefined. And I'll show you an example of that here in a second. But let's finish this one. So we need the derivative. So let's go ahead and do it. So let's go ahead and I would distribute this first, rather than do a product rule. That would be kind of ugly. What do you get when you take x to the 2/3 times x? Got to add the power. X to the 5/3. Okay, so that's our f function. So now I'm going to do f prime. So I bring down the 2/3, that'd be 10/3. This is no calculator now. X to the what? Negative 1/3. Okay, minus, now I bring down the 5/3, that's still 10/3. X to the 2/3, right? We subtract 3/3, subtract 1. Now we're going to set that equal to 0. Now we're also going to keep in mind that we're thinking about where f prime is undefined also. Right? We're thinking about where f prime is undefined, but right now we're going to worry more about where it equals 0. Okay, wow. What do we do with that mess? No. Right, but it'd be kind of like putting this together. Can I put x to the 5th minus x squared together? Got to be like terms. The powers have to be the same to be like terms, right? So what would we do with x to the 5th minus x squared? We take out an x squared. Well, now why an x squared? Why not an x cubed? They both have to have it. So what it ends up being is you take out the smaller power, right? Well, that's what we're going to do here. We've just never done it. I don't even know if in Algebra 2 you ever did this with fractional powers. Maybe you did. I don't know. And with a negative, but it's the same thing. The idea is you just take out the smaller of the two powers. So let's take out a 10/3, and let's take out an x to the negative 1/3. Now, before we do it, it's really just distributive in reverse, but you think about when you distribute, if you add the powers, well, when you factor out, you subtract the powers. So up here, when I take out x squared, what's left? Well, we just had 5, we took out 2, so we have 3 left. It's a subtraction. And of course, if you take out all of something, then there's just a 1 there, right? Well, we do the same thing here. So on this first one, I took out everything that's there. What's left? There's a 1. Here I took out the 10/3. And what power do I have left? Well, I had 2/3. Yeah. And I took out a negative 1/3. I usually just go off to the side and write it just to be sure, but you'd be amazed how many times it just comes out 1 or 2, a whole number. So we had 2/3 here. Just like here we had a 5 and took out a 2, so we have 3 left. We had 2/3 and we took out a negative 1/3. Well, that ends up being 3/3 or 1. It ends up being just x to the first, which is really nice. Most of the time they work that way. But they love to put these on the AP test. I'm surprised it took us 4 packets to run into one. They love to put these on here because these cube root functions are ones that have vertical tangents and weird things like that where you have the derivative undefined. Like, look at that. There's a change in concavity there, an inflection point. Now, it doesn't change in increasing, decreasing, but it could, right? You could have those situations. Okay, anyway, where does that equal 0? Well, where's this equal 0? The parentheses. When x is 1. So that's one place. What about this over here? This would be, yeah, this would be 10 over 3x to the 1/3. That negative power would flip to the bottom. That'll never equal 0. But it is undefined when x is 0. So if you forget about that, so that 0 needs to go on our number line. Okay? So let's do that in red. Let's put the number line over here. So we got f prime. I got to make sure and label it. And we got to put both a 0 and a 1. Now, if you would have forgot the 1, chances are you would have come up with C as your answer. If you only would have went with the derivative is 0, you might have come up with C as your answer. All right, so let's pick some numbers here. So negative 1, let's do 1/2, let's do 2, and let's plug them into this version of our f prime. Well, actually, this first part, I'll probably use this version down here. Okay, so let's put in negative 1. Well, negative 1, what's the cube root of a negative? Negative, right? So we have cube root of a negative. That'd be negative with that stuff. That would make that negative. If I put a negative 1 in here, we'd have 1 minus negative 1. That's positive. So we'd have negative times positive, which is negative. Okay, let's put a 1/2. You put a 1/2 in cube root, that's going to be positive. 1 minus a half, that's positive, so both positive. And then we put in a 2. 2 to the cube root of a positive, again, is still positive. 1 take away 2 is a negative. Positive times negative is negative. So there we go. So it says, where is f increasing? Between 0 and 1. Okay? All right, so if you graph this, though, what you'd notice is some weird stuff. You'd notice like a sharp point. You'd notice a couple things. You'd notice a place where the derivative is 0, right? So it would flatten. You would have, that's at 1, you would have a local max, but you would have a sharp point here. So you'd have it coming down, sharp point, then going up, and we've seen those functions before. It comes down something like this, and then goes something like that. So we do have a local min and a local max, but they're for different reasons. Okay? All right. So that's 23. Now, I wanted to show you something here when it comes to the chart. So I've got a function here, okay, that I've put up here, just a basic old 1 over x. Now, you should know this function, but let's say you don't. But usually they give you something a little different. But and this is very similar to the last free response question on the previous pack, okay? Except it's got some A's and B's in it, but it's similar. So you look at this function right here, okay? Now, let's say we didn't know what this graph looked like. And you were asked, where is this graph increasing? Like we just said. Well, where do you look? Well, you want to see where it starts and stops increasing, so that'd be when the derivative is 0 or the derivative is undefined. So we do a number line. So we would do our derivative, and we'd come up with this. So what would we put on our number line? Is this ever 0? No. But it is undefined when x equals 0. So we put a 0. So let's put a -1, let's put a 1 in. So we put a -1 in here and you square it. That's 1. 1 into -1, negative. Let's put a 1 in there. Put a 1 in here, squared is 1. Oh, it's still negative. Now, think about this a minute. Pretend you can't see this, right? Pretend I just gave you this number line and asked you what's happening on the F graph. What would you have said? Chris? You think so? If we hadn't been talking about this undefined business, and I just gave you this number line and said, what's that tell you about F? I bet you'd have said flat spot. Does this graph have a flat spot? It doesn't, does it? But what we really mean is it's decreasing, then it keeps decreasing, right? But what's happening here, see, because for a long time we weren't worried about functions that were ever undefined. We were sticking with nice, smooth ones where cool things or nice things happen that made it, easy for us. But now we got to consider, we're far enough into this, and we got to consider what happens if we have these undefined spots and so forth. So we got to consider it. So what we really have is a function that's decreasing, then keeps decreasing. Well, of course, the reason is because 0 is undefined in the original, right? So we can't have a flat spot where there's no spot, right? There's not a point there. So we can't have a flat spot. And then you look at this graph, sure enough, decreasing and then still decreasing. Okay, now let's go to the second derivative. Now let's say the question is, where is this graph concave down? Two different questions. Where does the graph concave down, or where does this graph have an inflection point? Let's say we have those questions, because that's what that one on the packet is. Well, you do what for concave down? Second derivative, right? So we would do the second derivative. So here it's negative x to the negative 2. So we'd bring down negative 2. That'd be positive 2, x to the negative 3, which would be this right here, right? 2 over x cubed. Where does that equal 0? Never. But it is undefined at 0. So let's put in a -1 and a 1. And so I put a -1 in here and cube it. That's negative. Into a positive, that's negative. Put a 1 in. 1 cubed is 1. 1 into 2 is positive. Now, pretend, a month ago when we were doing charts or whatever, I just give you this chart, F number, or this number line. F number prime looks like that. What would you have said? You just said inflection point. We got concave down, switching to concave up. Does this graph have an inflection point? No. You can't have an inflection point where there is no point, right? Because the original is undefined here as well. You do have a change in concavity, right? Look at this. Concave down, concave up. But there's not an inflection point. So the question was, where's this graph concave down? Yes, the number line would be good. Less than 0. Where's this graph concave up? Greater than 0. Okay? Is there an inflection point? No. Right? So that's what this idea of where f prime or f double prime is undefined comes in, and what it would look like on a number line. And we have to consider it with what's going on. Okay. I wanted, because that showed up there with that problem, and so I wanted to make sure we've talked about it before, but we haven't really done a lot of problems where that was an issue or where that was involved. Okay? All right. Perfect. Rest of the time is yours to work. I got a couple of answer packets, answer books up here for the new packets. The last two, this is for the previous two. Midterm tomorrow, no calculator. I will hand in the first 2 packets. Okay? I have some extra read out order forms for the shirts for the American Heart Association fundraiser and the read out basketball game on February 13th, so if anybody needs one. POSA is selling them. Yep.
So I got to K equals.
Yeah, I don't know if you want to do that. Because you're looking for x-intercepts, right? Which would be when y is 0. So I see why you set that equal to y. So you might hang on to that. That might be worth something. This is similar to another problem we did earlier. What you have is a cubic. And cubics typically do something like that, right?
Yeah.
Now, where will this have 3 distinct x-intercepts? Do you remember this? Because if I shift this down, because k is really the vertical shift.
Yeah.
So if I shift this down to where this point goes below, I'm not going to have 3 anymore.
Yeah.
Or if I shift it up where this point goes above, I'm not going to have 3 anymore.
So you need to find your max.
I got to find my local max and mins. Then when I find what those x values are, because what's happened when you do the derivative, k will disappear, right? So you do the derivative, set equals 0, find your local max mins. Then take those x values, plug them into the original to give you this y value. And you want this, the max's y value, you want to be greater than 0. And the minimum's y value, you want to be less than 0. So it'd be that kind of thing, and then that's where you'd run it.
Okay.
Make sense?
Yep.